Hello students. Hello students. Welcome back once again on our series of live session on atomic structure. I am Shubham Patel, your chemistry faculty from Tutoratti, and this session is brought to you by Tutoratti. And since the starting we have done 2 sessions, and this is the 3rd session in the series. In the previous sessions we have studied the basic models of atoms. Those were Thomson's model and Rutherford's model, and the experiment done by Rutherford. And it is very good to know that this session is really helpful for you guys, and we are having a good response from you guys. It's really good. I'm very happy that this session is helping you in a way, and this is the core purpose. So we will begin today's session and start the EMR, that is electromagnetic radiation, and the photoelectric effect in today's session. So whenever you guys can hear me and see me, please tell me so that we can have a better interactive session. Hello Jayant, how are you? As soon as you guys can hear me, join, click, just tell me. How are you? Sab badhiya? This is the 7 PM, so this is the time of study. You must have had your snacks and all. You must have played, and this is the time for study. 7 to 8, 9. Hello Pranit. How are you? I hope you're doing well. So let's start today's session. It's Maxwell's theory of electromagnetic radiation. Let's rewind a little, recap. Why are we studying Maxwell's theory of electromagnetic radiation? Why? Because in the last session, we got to know that Rutherford's model has some drawbacks. It was not foolproof, it was not very good, but at least, that's very good to know, Pranit. At least we got to know that an atom has a nucleus, and from today onwards we are going to know about the electromagnetic radiation. Now in the initial, after this session we are going to know about Bohr's theory, because after Rutherford, Bohr explained the atomic model in a very good way. But the current model, which is the quantum model, is explained by quantum theory. And quantum, or the basis of all these things, is electromagnetic radiations. So electromagnetic radiation, which is a radiation, we are going to start with that. Let's begin with radiation. What are the sources of radiation? You must know a very common source of radiation, जहां से आप सबको radiation मिलते हैं. The entire world has, or I can say at least the entire solar system gets the radiation from the source. Can you tell me what that source is? Tell me. What can be that source? You guys are very correct. The source is sun. Now if you imagine the sun, you don't have to imagine it, you have already seen it, but if you just imagine it, what are the things that come to you in your mind? The first one is object at high temperature. Sun is at very, very high temperature. Hello Sarthak. I hope you are fine. Yes Pranit, it is sun. The sun is at very, very high temperature. So for the radiation, the important thing is the object should have very high temperature. And the second one is accelerating charges. And we all know that from sun we get the accelerating charge particles in the form of solar flares and ions and other radiations, so many things. So these two things are very required for the radiations. Exactly. So electron, as per Maxwell's theory, In the last session, I told you that electron loses its energy continuously. Who told that? Not me. Do not blame me for this. Electron loses the energy continuously, and Maxwell told us that electron loses this energy continuously. I'll tell you today what are the problems with this model also. But for now, we know that electron loses its energy continuously. Maxwell told us this. The next thing, how the electron loses its energy is like this. If electron keep on losing the energy, it will follow the spiral path and fall back into the nucleus. Okay? So, electron will lose energy in a continuous manner. Who told us that? Maxwell told us that. Why am I repeating it? Because it is very important to know that Maxwell said this. Okay. The next thing is, what is the meaning of continuous here? I am saying that electron loses its energy in a continuous manner. Or Maxwell told us that electron loses its energy in a continuous manner. What is the meaning of continuous? It means the energy, the wavelength of energy or the frequency of energy does not change. If the wavelength or frequency will not change, the energy will be in continuous motion. If it changes, the energy will not change in continuous manner. I hope you got the point. Okay. The next thing, this was the Maxwell theory which I was explaining. I hope it's very clear to you. The next thing is, what is electromagnetic radiation? I hope you must know, or at least you have some idea about what are electromagnetic radiation. Can you give me an example of what electromagnetic radiation? Just an example. Basic example will suffice. Tell me. Any example? Yes, light. Exactly. Electromagnetic radiation, light is an example of electromagnetic radiation, that is EMR. Okay. So what are EMRs? What are electromagnetic radiation? The radiation in which electric field and magnetic field oscillates perpendicular to each other and both perpendicular to the direction of propagation. सर बाउंसर मार दिया, इतने सारे jargons. Electric field, magnetic field, that two propagating perpendicular to each other and perpendicular to the direction of propagation. So many things. How will I understand? You will understand by this. Cool, huh? Just like machli jal ki rani hai. Yeah? Electric field is propagating in this direction. The magnetic field is propagating in this direction. Not dancing, just showing you. Magnetic field, electric field is propagating in this direction. And magnetic field is propagating in this direction. Just like snake. And both of them are moving perpendicular to the direction of propagation, because the direction of propagation is, if you see from here, the direction of propagation is this, and one is oscillating this way and other is oscillating this way. Both the directions are perpendicular to the direction of propagation. Okay, so I hope you must have understood. Electromagnetic radiation has two components, electric field and magnetic field, and both are oscillating perpendicular to each other. I hope you must have got it. So the next thing, direction of propagation, how do we get it? We get a cross product of electric field and magnetic field, by which we can tell the direction of propagation. Okay. What are the characteristics of transverse wave? Transverse wave, earlier the waves we saw were transverse wave. What is the transverse wave? Here, see, it's a source, a vibrating source, which oscillates perpendicular to the direction of its propagation. जहां उसको जाना है उसके perpendicular direction में move करेगा. It moves or oscillates in the direction perpendicular to its direction of propagation, like this. Look at it. Here, मस्त snake है. है ना बढ़िया? If you see closely, the particle is oscillating in this direction, in the vertical direction if I say, and the wave is moving in this direction. So both the directions are perpendicular to each other, and that is how the transverse wave forms. Okay, we will know about the various components of various forms of transverse wave. What are those? The topmost point of a transverse wave is called crest. Pizza ka crust nahi, it is crest, CREST. That is different. मुंह में पानी नहीं लाना, स्नेक करके बैठे हो, ठीक है? This top point is crest, and the belowmost point is called trough. Trough. This is crest, this is trough. Crest is the top point, trough is the below point of a transverse wave. Let's move ahead. And transverse wave have these properties: amplitude, wavelength, time period, frequency, speed, and wave number. We will get to know about each of them individually one by one. I hope it's okay. एक एक करके सब जानेंगे. The first thing is amplitude. What is amplitude? Amplitude is the maximum distance or maximum displacement from the mean position. ये mean position, maximum displacement, like this. This is the mean position, the middle line, and the displacement, maximum displacement is here, the red point. So the distance between this mean line and this red point is called amplitude. Okay, this amplitude, generally it is described by A. Okay, and this is also A. Whether we check from the upside or downside, both will be amplitudes. Okay, the height of the crest and the depth of the trough will be called, yes, it is called amplitude. Amplitude can be measured in meters. Generally the wave is very smaller, so it is measured in, we can say, nanometer, picometer, anything. Okay, transverse wave. The second point is wavelength. What is this wavelength? You must have seen it in the earlier okay, what you can say, JPG also. The wavelength. What is wavelength? Here, distance between two crests and two troughs. This is one crest, this is one crest. The distance between those will be called, two consecutive crests will be called wavelength. Why am I using the word consecutive? It means if I say distance between two crests, some notorious student will going to calculate from this to this. He will say, you said crest to crest. I said two consecutive crest. From this crest to this crest. From this trough to this trough. The distance will be called wavelength. Whether this or this, the distance will be called wavelength. It is also measured in generally in meters, but the wavelength is very smaller, so it is measured in nanometer or generally in angstrom. Okay, it is described by lambda. ध्यान से देखिए इसे, क्योंकि this is going to be very helpful. This is going to be very common symbol in your upcoming studies. Okay, the next thing we want to study is time period. What is time period? Time taken by the wave to complete one oscillation. Let's see. What oscillation? Look at this red dot. This. Again, time taken by the dot to cover this one oscillation. One oscillation is this. From this point to this point, time taken by the wave to complete one oscillation will be called time period. Okay, time period. Do not ask me how will we measure time. I will say इंची टेप लेके आओ, माप लो. But time है, we'll measure it only in seconds. Okay, it will be measured in seconds. The next thing is radiations. The fourth point of this discussion is going to be frequency. Now, you all must have heard about frequency. Okay, frequency. What is frequency? Number of oscillations in 1 unit time or in 1 second will be called frequency. Number of oscillations. 1 second में wave, how many oscillations does the wave cover is called what? Frequency. Or the second definition you can also understand by it, that number of waves passing through one point in 1 second will be called the frequency. How is it represented? By nu. Okay, this is called nu. Nu, just like nu. It has a zing in it. And what is the unit? Unit is hertz or cycles per second, generally per second. Okay, cycles per second. So, how many properties do you have studied till now? 4. What are those? Can you tell me? What are those properties? It was amplitude, wavelength, time period, and the fourth one is frequency. Okay. Here, frequency, as your unit says, cycles per second. Cycles per second. Cycle is the number. It will not have any unit. So the unit will be 1 upon time. That is per second. Hertz is equal to per second. Okay. The next point is speed. What is speed? How can we calculate speed of a wavelength? Speed it means what is the length of the wave divided by the time period or the time taken by wave to complete that length. How do we calculate length in the form of a wave? Yes, it is in the form of lambda, and the time period is t. So the speed will be what? Lambda upon t. Simple as that. Distance travel is lambda, time is t. So it will be, yes, lambda upon t. And wait a minute, this is lambda. What do we call 1 upon t? What do we call it? We have studied just right now. 1 upon t is called nu, frequency. So lambda into frequency is speed. And what is the speed of light? Can you tell me? Just tell me, what is speed of light? Anyone? Sarthak, Pranit, Jayant. Just tell me. Very good, Sarthak. Yes, Pranit, you are quite right. It is 3 into 10 to the power 8. And what is the unit, beta? Meter per second. Exactly. 3 into 10 to the power 8 meter per second. So this is the light. This is the speed of light which is applicable. Okay. So the last thing which is left is the wave number. What is wave number? It is the number of waves present per unit length. Number of waves present per unit length. Now, number of waves again will not have any unit in it. Number doesn't have any unit. Good, Sarthak. Number of waves will not have any unit, but length has a unit. So 1 upon meter will be the unit of wave number, and lambda also has unit of length. So I can say The wave number is represented by nu bar. How do we read it? This is nu and this is bar. This is represented by nu bar and the unit is centimeter inverse. It means nu bar is equal to 1 upon lambda. ये formula याद रखिएगा. It is very important because you will confuse if somehow it comes what is the wave number. If you do not remember 1 upon lambda, so many formulas, this will be used as such. Okay, so wave number is 1 upon lambda as per the definition. So we can also say that wave number is the reciprocal of wavelength. You can say it is quite correct. So this is the main formula. Let's move ahead and we have a problem for you. This is the question. I will give you 1 minute to solve. Vivid Bharati station of All India Radio Delhi broadcast on a frequency of 1368. This is very important. 1368. This is 1368 kilohertz. What is the wavelength of the radiation? I will give you 1 minute. Solve it and tell me the answer quickly. So how do we calculate it? Look at here. This is the formula that we have. Frequency into wavelength is equal to C. We have C. Do we have frequency? Yes, this is the frequency 1368. But do not forget this small k because this will cost you dearly. This k stands for kilohertz. It means when you will write the frequency, value of frequency, you will write 1368 into 10 to the power 3 as the frequency, and C you already know, 3 into 10 to the power 8. Here, look at this. Lambda is C upon nu. Okay, this is 3 into 10 to the power 8 meter, and the frequency is, yes, 1368 into 10 to the power 3. Just divide it and you will get the value, that is approximately 2.2 into 10 to the power 2 meter. Wavelength 2.2 into 10 to the power 2 meter, which is quite a large wavelength. So the All India Radio broadcast at a very large wavelength. Okay, good, Sarthak, very good. Should we have another question? I think we should have some practice. Okay, so let's start with one more. Have a go at this. Very good, Pranit. Yes, Sarthak, give me the answer of this question. Calculate the wave number of a radiation having wavelength 5800 angstrom. It is very quite easy question. You have been given the wavelength and you have to calculate the wave number. Wavelength, wave number. I have just told you an example. I have just told you the formula. Yes. Sarthak is on fire. Great. So what is the solution? Wave number is 1 upon lambda, 1 upon wavelength. Just put the wavelength. 1 upon lambda. Just write the value. Lambda is 5800 into 10 to the power minus 10. Sarthak. Look at the power of the 10. Look at the power of the 10. Pranit. It will be 1.7 into 10 to the power 6 per meter. What happened? Just we have divided 1 by lambda, that is 5800 into 10 to the power minus 10, and then solved it. So you have found the problem that the student are going to make the mistake here. This is 10 to the power minus 8. It will go upward. It will be 10 to the power 8. Okay. So do not make this mistake. It is in positive, not in negative. It is in positive. Okay. Should we move ahead? I think. Good. Okay. So the next one is electromagnetic spectrum. Here we are going to study about electromagnetic spectrum. What is this spectrum means? ये electromagnetic spectrum क्या किस तोते का नाम है? Oh, speed के चक्कर में silly mistake कर दी. Yeah, that is important. I have told you several times that speed is good, but consistency and making the right answer is very important. Okay, nobody is going to award you that you have completed the paper in 2 hours instead of 3. You will be awarded for your correct answers. So do not make mistakes. Okay. Welcome, Meena. What do you mean by electromagnetic spectrum? So what is this electromagnetic spectrum? If I arrange the electromagnetic radiations by wavelength or frequency, then I am going to get a spectrum. If I arrange them by wavelength or decreasing frequency, decreasing wavelength or decreasing frequency, I am going to get a spectrum. So this is the spectrum of light. The entire radiation, this is your spectrum, and this is everything. Yes, that's quite right. Spectrum of different wavelength. If I am using the same wavelength, it is not going to be present in spectrum, Sarthak. So yes, different wavelength, it's quite correct. This is the spectrum. From gamma rays to long radio waves. Why are we studying this? Because there was a direct question asked in JEE 2019 from X-rays. Direct question. You just had to know what is the length of wavelength at X-rays, at around X. Just direct question. So the first one is gamma rays. The first one is gamma rays. What is the length of gamma rays? What is the length of wavelength in gamma rays? It is around 10 to the power minus 14 meter. This is in meters. 10 to the power minus 14 meters to 10 to the power minus 12 meters. Very small wavelength, very small. And the next one is X-ray. X-rays, we all know about. Whenever we have broken bones, we get X-rays. Those X-rays have a wavelength of about 10 to the power minus 10 meter. 10 to the power minus 11 to 10 to the power minus 8. I can take the median as 10 to the power minus 10. This is the range, and you have to understand. If I want this to be in angstrom, how much will it be? It will be 10 angstrom. Okay. Next is ultraviolet light. We all know that how harmful UV rays are. We all wear sunscreen to protect ourselves from the UV rays of sun. Those UV rays have a wavelength of about 10 to the power minus 8 meters. It's the median range, which is about 10 to the power minus 8 to 10 to the power minus 6 meter. X-rays. And what is this red region? क्या है ये? This red region is actually the region where we can actually see the light, because in all those regions, gamma rays, X-rays, UV rays, you cannot see those. You cannot see, oh, the X-ray is going on, I should catch it. No, it is not like that. You cannot see. You can only see the light in this region, which is the, as rightly called, visible region. And what is present in visible region? Yes, in the visible region, we have different colors. The light is present in different color, or I can say every color, every different color has, yes, Pranit, every color has a different wavelength associated with it. The maximum wavelength will be for, yes, the maximum wavelength will be for the red color, and the minimum wavelength will be for violet color. That is why we have red lights on the top of a building, so that a very far helicopter can also see it, because its wavelength is quite big. Okay, we can see the red light from very far, but we cannot clearly see a violet light from very far. That is the beauty of wavelength, nothing else, just the wavelength. Okay, if we move ahead with this, one thing is important, that you have to remember the range of this visible region. It is 400 nanometer to 750 nanometer. You need to remember this. You need to remember this range. Okay. Next thing is, next to visible region is infrared region. Infrared region has a value of wavelength is minus 10 to the power minus 6 to 10 to the power minus 3 meter. This is the median range will be 10 to the power minus 5 meter. Yes, Tanishka, it is the red region. It's quite right. Very good. Now the next thing is microwave. Microwave, the wavelength in those in that region is around 1 meter. Quite large. And just we have, in the earlier example, we saw that the radio broadcast has a wavelength of about 200 meter. So we have radio waves, that is FM and AM. Can anyone of you tell me what is the full form of FM and AM? Those come in the region of radio waves. What is FM and AM? Tell me, guys. Radio waves have a wavelength of about 1 meter to 1000 meter. In the example, we got around 220 meter, which is quite right, because the range is that only. What is the full form of FM and AM? Quickly. Tell me quickly. Jayant has told us as amplitude and frequency modulation. Pranit has also told us that frequency modulation, which is very correct. It is actually amplitude and frequency modulation. Very good, Pranit and Jayant, both of you guys. Let's move ahead with this. After that, we get long radio waves. Okay, long radio waves. This is the entire electromagnetic spectrum. I will give you guys 30 seconds. Yes, Sarthak, you're quite right. I will give you guys 30 seconds to note it down, because it is very, very important. I'll move aside and give you time for about 30 seconds. Write it down. Noted? Very good. So the wavelength increases in order. This is the actual order, which we already know by now, that gamma rays has minimum wavelength, after that X-rays, then UV rays, then visible, then IR, then your infrared, microwaves, radio waves, long radio waves. This is that. Now I told you in the earlier session, in this session, that Maxwell, I am not saying anything, Maxwell is saying. Why was Maxwell wrong? Because Maxwell told us that electron is losing energy in a continuous manner. Electron is losing energy in a continuous manner. What is the problem with this continuous manner? That in the two ways energy of electromagnetic radiation can be achieved, can be increased. We all know that E is equal to h nu and E is equal to hc by lambda. Either we increase the frequency and the energy can be increased, either we decrease the wavelength and the energy can be increased. It means I have to change either one of them or the amplitude. At least something has to be changed. But Maxwell told us, according to Maxwell, without change in wavelength or frequency, electron is losing energy. But the electron is not losing its wavelength or frequency. It means the light that electron is emitting, that light is not having any change in wavelength and frequency. Can this happen? Electron is losing energy continuously and the energy itself has no change in its wavelength and frequency. How can this happen? It cannot happen. And the other thing is that Maxwell told us that only the intensity of the light will change. Intensity of the light will change. Maxwell told us this. How can this happen? If intensity is changing and amplitude is not changing. Because if amplitude will change, then frequency will change. If frequency will change, then the whole concept will go down. And Maxwell itself is saying that only the intensity is changing and wavelength is not changing. And we know the intensity is directly proportional to the square of amplitude. So this cannot happen. It means Maxwell was wrong in this aspect. Exactly. Okay. One more important thing is that if you heat iron, प्रतिज्ञा कर लो, दिया जलाया, हाथ रखा, ऐसी हरकतें नहीं करना है, उस पे रखना है लोहे की छड़, वो भी सेफ्टी ग्लव के साथ. ऐसे पकड़ोगे तो दिक्कत हो जानी है. तुमने जलाई आग और उस पे लिखी लोहे की छड़. The rod is going to get heated. Initially, it will not show any color. It will just get heated. And after a while, it will show red color because it is heated. Red is the sign of danger. Danger. So that sign is of red color. Iron will get heated and that will be in red color. Now, how can I say that it is getting heated and its wavelength is not changing? Because earlier it was not showing any color and now it is showing red color. It means the wavelength is changing. It is definitely changing. That is why I am saying Maxwell was wrong in his approach. Okay. So what proved that Maxwell was wrong? There were two things that proved that Maxwell was wrong. One was black body radiation and the other one was photoelectric effect, which we will study tomorrow. But black body radiation is just what is the experiment we'll get to know today. Okay, what is this black body radiation experiment? It what is a black body? Black body is the subject or the object which can absorb all the radiation. Not only absorb, it can emit also all the radiations. See how you see colors. How are you seeing that this is a black color? It means this particular cloth is absorbing certain wavelengths and reflecting certain wavelengths. This black body absorbs all the wavelength and can emit also all the wavelengths. This is called black body. If I heat an iron rod, what will happen? If I am heating it at a temperature T1, this will be the graph of intensity versus wavelength. Suppose I am heating at a higher temperature. I was heating at 1000 degrees Celsius. Now I am heating at 2000 degrees Celsius. What will happen then? The intensity, the peak intensity will increase, and it will come at a lower wavelength. And what will happen if I increase further the temperature? The intensity will further increase, and it will come at a earlier wavelength. It means wavelength will become shorter and intensity will become higher. This was not according to Maxwell. That is how we got to know that Maxwell was wrong. Okay. Now, next thing. What was the black body radiation experiment that we have just got to know? That temperature, as we are increasing the temperature, the wavelength corresponding is getting diminished. It is getting minimum. In the earlier example, just again see the graph. We are increasing the temperature and the wavelength is getting minimum and minimum. Okay. So this was the black body radiation, and on the basis of black body radiation, Wien's displacement law came. This was Wien's displacement law. It says that lambda maximum into temperature will always be constant. Lambda will not be constant, temperature will not be constant, but lambda into T will be constant. This is Wien's displacement law. Shall we practice a question on this? Okay, let's have a question. This is your problem, and try it. I'll give you 1 minute. I'll step aside. Okay, so what are the factors that we have here? Here we have that the temperature is, maximum temperature is 1500 Kelvin, and it emits, what is the wavelength? 7000 angstrom. Okay, Sarthak has given an answer. Let's see whether he is correct or not. What will be the maximum wavelength if the temperature is increased to 3000 Kelvin? One wavelength is given to you, other one they are asking. One temperature is given to you. Okay, Tanishka has also given an answer, and both are different answers. So let's see which of them is correct. Let's see. What formula will be used here? I have just told you that what is the relationship between lambda and T? The relationship is Wien's displacement law. Lambda maximum into T is equal to constant. It is just like you can use like Boyle's law. What? P1 V1 is equal to P2 V2. You can also write it as lambda 1 T1 is equal to lambda 2 T2. Let's have it. This is lambda max into T is constant. Lambda 1 T1 is equal to lambda 2 T2. Just put the values. And when you put the values, the answer will come. It's quite easier, I guess. The answer will be 3500 angstrom. So both of you are correct. It's very good to know that you are on a good pace. It's very good to know. So we have practiced both of these questions and we have come to an end of today's session. In tomorrow's session, we are going to study the photoelectric effect. Devansh, my name is Shubham Patel. Thanks for asking. In tomorrow's session, we are going to know about the photoelectric effect, not tomorrow, day after tomorrow. We'll have a session on Wednesday, not tomorrow. So stay tuned with Tutoratti, JEE and NEET channel, and make sure to like, share and subscribe the channel and be there in the next live session. If you haven't seen the previous videos, go to the channel and revise it. And thank you.